My dear friends, welcome to Rajashekar classes on applied data science with Python. This is lecture number 454. In this chapter, we will cover a bunch of miscellaneous topics from various aspects of machine learning. The first concept that we will cover is called calibration of models. Before we go and understand various calibration algorithms, let's understand why we need calibration and in which context it is useful. So let's take a simple example of two-class classification problem in which my yi, what is two-class classification problem means, your yi belongs to 0 comma 1. Let's assume I have a data set, my data set d equal to xi comma yi, and I have trained my model using this particular data set. Let me say this is my training, d is my training data set. I called my model f of x, isn't it? My model is f of x. Let's call this model f of x. Now given a query point xq, what do I get? I get f of xq as my yq, isn't it? Because that's what the model is. Sometimes in the real world, I want to actually use not just yq. I want to actually use not just yq, not just yq value, but sometimes I want in binary classification setting. I just don't want to know whether the class label is 1 or 0. I will repeat, I just don't want to know. I just don't want to know whether the class label 1 or 0, but I want to understand the probability. I want to understand the probability of yq equal to 1 given xq, obviously the model f, and what the model returns to me, yq, your yq may or may not be, this model returns that return value may or may not be this will return some probability. This may or may not be the exact value. Exact value. That is the difficulty, isn't it? We will try to understand this with simple example. If you take naive-Bayes classification algorithm, just try to recall naive-Bayes algorithm. What does naive-Bayes do? It exactly does this. Probability of yq equal to 1 given xq is proportional to probability of yq equal to 1 multiplied by product from I equal to 1 to d. This formula we already learned in our naive-Bayes classes. This is for each dimension. For each dimension, or I can say for each feature, isn't it? Similarly, I have a probability of yq equal to 0 given xq, isn't it? This is, I have another probability. I have two probabilities. This is what I will compute, isn't it? Now, I will say that it belongs to class 1 if probability of yq equal to 1 given xq is greater than probability of yq equal 0 given xq. We have seen all of these in naive-Bayes classification algorithm, but we are not giving exact probabilities. Here we are not getting exact probabilities. This is not exact probability, isn't it? It is proportional, not equal. Here you don't have any equality, proportional. But we are not getting, I can say, not giving exact probabilities. Exact probabilities. Why? Because they are proportional, not equal. These probabilities are only proportional, isn't it? These probabilities are only proportional to this. We are not exactly equal. We are not getting exactly equal to this. So the question we have here, the question of calibration, the big task of calibration of model is given a model f which takes xq. Given a model f which takes xq as input and returns which takes xq as input and returns yq. This yq may or may not be the actual probability of yq equal to 1. This probability may or may not. That's what we are saying. May or may not be the actual probability of yq equal to 1 given xq, isn't it? So given this model, isn't it? F of xq is model. So given this model, I already have trained model. Given a trained model, give me a method through which I can compute probability of yq equal to 1 given xq. Similarly, I can also calculate another probability of, it is binary setting, isn't it? Yq equal 0 given xq. I can always calculate these two probabilities, isn't it? I want the exact properties. Here problem is I want the exact properties. I want the most, I want exact probabilities. I want most appropriate probabilities. I just don't want some number. Any number between 0 and 1 can be written by using sigmoid function, isn't it? That's not what I want. I want actual probabilities. I want actual probabilities. I want the actual probabilities itself. You might ask this question, why do we need all of this? Why do we need calibrations? Since we understand what is calibration, calibration is a stage. What is this calibration? Calibration. This one is stage in machine learning. Calibration is stage in machine learning where given that you have already trained the model, isn't it? You have already trained the model. We are trying to calibrate it such that you get the actual probabilities of class 1 and class 2, isn't it? Why do we need this calibration? To get actual probabilities. Actual, not proportional, isn't it? It's something like that. No, you might wonder, why do we need probabilities exactly? Isn't it? Let's assume my loss is log loss. Let me assume my loss is, what is my loss? Let me assume my loss is log loss, isn't it? Let's assume it is 2 class log loss. Then how does my 2 class log loss looks like? My 2 class log loss is equal to, 2 class log loss equal to minus 1 by n into sigma I equal to 1 to n yi log of pi plus 1 minus yi into log of 1 minus pi. What is this pi? Pi is probability. Pi equal to probability of yi equal to 1 given xi, isn't it? Remember this formula, this log loss which we use a lot in machine learning, depends on the actual value of the probabilities. This particular log loss depends on actual values of probability, isn't it? I will repeat. Remember this formula, this log loss, which we use a lot in machine learning, depends on the actual value of the probability your yi is 0 or 1. If I get my probability value wrong, this whole log loss we compute is wrong. If you are using log loss as a measure of performance, which we use a lot in real world situations, we have bunch of case studies in which we clearly explain why log loss is right metric and accuracy, AUC or any of these matrices. Log loss is very critical, especially for two-class classification, even for multi-class classification. If I have to pick one type of loss which is used the most, one is log loss. Log loss will be the one, isn't it? Now, for log loss, we need exact probabilities. That is important. For log loss, we need exact probabilities, isn't it? Exact. For log loss, we need exact probabilities. But if your model is returning a function, like like this f of x equal to yq, yes, returning what is your function doing? Given xq, it returns yq, isn't it? Now, what I need to do is, on top of this yq, I need to build another calibration model that takes yq. Just see, that takes yq and returns probability of yq equal to 1 given xq, isn't it? What is this? This f of xq equal to yq, standard classification model or some regression model. What about this calibration model? This is your calibration model works on yq, isn't it? That is output of that model. Train a model f on all of your data, and given a query point, this main model returns you. What is your main model returns? Your main model returns yq, isn't it? Main model will return, this will return yq. But what I need to predict is probability of yq equal to 1 given xq. That's I want to predict. That's what calibration helps me to achieve through bunch of very neat mathematical tasks. Just go through this lecture. If you have any difficulty, please keep a comment. Thank you very much.